So part one, give the function f of x in the lines y equals k and x equals j. As shown in the figure below, write an expression for the length of each of the given segment in terms of f of x, f of y, j, k, or some combination of these. So, now, they want to know what the length of each of these segments. So we have AB here, okay, CD here, EF, and we have GH, IJ, and AL. All right. So now we have, okay. How would you find the length of AB? In terms of f of x, f of y, j, or k?
Oh, wait.
First of all, if I want, let's actually pick an easier one. Let's do the second one. How would I find CD?
Y
F
F of C.
of x.
What is F of X?
What is f of x? What is our y is equal to f of x, right?
Oh, wait.
Why
The function is the big line.
Yeah, my function, this big line here is the function, is f. All right. So if I wanted C or CD, I would just find f of x at that point, at D. Okay.
F of D.
Well, not at D, it's just that's the endpoints of those segments. Okay. So whatever value is that x value.
Is that A and B equals
X. No, it's F of X.
Now, why is CD f of x? Because that's the height, right?
Yeah.
The height is y. AB is the width. What's the width? X. And what is x equal to? F of y.
Wait, what's the point of? Oh, I see what they mean.
Yeah.
So x is equal to j is a function. Is x equal to j? What is y is equal to k?
Yeah, those are functions. Those are functions, yeah.
All right.
Where is F of Y? Oh, we just made it up. Wait, so for the
Again, this big function, the color out. So this big function right here, this is the function f of x if I'm looking at it what? If I'm looking vertically to find y, it's f of x. If I'm using my x-axis to plug in values, to find my y value, I have f of x. But we use for AB, we use f of y because now I'm using my y values to find my length of x. Okay, so the idea here is if I'm looking for a vertical line, my function needs to be in terms of what? X. If I'm looking for a horizontal line, my function needs to be in terms of y. That's what we need to know from this. All right. Now, EF is in purple. All right. Now, EF is vertical, so it should be, actually, what is it? So I'm looking for y, the y value, right? E just k. Because y is what? F of E here, y is k. That's the length of y is k. The height of y.
That makes sense because it's k minus 0.
Oh, and then G of H is K minus X.
Like, oh, and homogeneous.
That is correct. G of H. Let me get my green one out here again. G of H. All right. Is K, because this right here is K, minus f of x. Sure.
Point. Is H a point or a, what is H?
So
This represents non-energy.
H is I can start sneezing and tell you. Well,
Oh, wait, never mind.
But I don't.
Oh, yeah.
so let's look at IJ.
J. Who's J?
All right, it is just J.
And then J minus F of Y. I don't know.
Let's see, it wouldn't be that, it would be f of y minus j. Because it's got to be the higher function minus the lower function.
Yeah. No. Option one.
Yeah. Now, the purpose of this exercise is to go through the steps. If I am rotating around a vertical line, okay, if I'm rotating around a vertical line, then the width of my shape needs to be in terms of y. Okay, so let me show you here. Let's say I'm just taking, we'll make it real simple. Let's just say I'm just taking f here, and I'm going to rotate this function. We'll go from 0 to 2. Okay, so from 0 to 2. And I'm going to rotate this around the y-axis. So I'm rotating this around x equals 0. Okay, so I'm going to take this shape, and we are going to rotate it around, making like a bell shape. Okay, now the width of my shape is what?
4, 2. The radius is 2.
F of y.
Obviously. No.
The radius of my shape. So that means my function needs to be in terms of f of y. So when rotating around a vertical line, my functions need to be in terms of
Y.
y. When rotating around a horizontal line, my function needs to be in terms of x.
Oh my God.
So when rotating around a vertical line,
Round a part line.
the function needs to be in terms of y.
Y. Okay.
And then the opposite when rotating around a horizontal line.
Wait, so are we only looking at the line right now?
Yeah, we were just looking at that. Right? Now, if I was looking at f and g, now if I was just looking at f, that would create one solid figure, right? So I just worry about f of y, and that would be it. I don't have to worry about anything else. But if I was rotating both functions around, then I would have to do what? F of y minus g of y. So that's called the washer method, is when I have two functions, and it's going to create a hole in the graph.
Wait, isn't
Not when it comes to rotating around x equals 0. The furthest from that y-axis would be f in that case. So again, the height would be, if I was rotating both shapes here around this line, this would be the distance here.
so whichever one farthest to the right is the upper function?
Farthest from the line of rotation, yes. Because again, the real fun starts when I'm not rotating around an axis. What if I'm rotating around x equals 4? In that case, what is this radius here?
Oh,
4, right?
So that'd be 4 minus g of y. All right. What would this radius be?
Oh wait, I misinterpreted there. That would be 4 minus
F of y.
4. Yeah.
So you would end up doing, if I was rotating that around that, I would take my outer radius, 4 minus g of y, minus 4 minus f of y.
yeah.
Upper function is whichever,
Is the furthest from the line of rotation.
and then you subtract the lower function from.
Yeah, if I have a lower function, yeah. So here are the two methods. The disk method. Because all my shapes, if I'm rotating this, what is my overall shape going to be? Circle. So I need pi r squared, okay, times the height. Or times the width, really. Okay, pi r squared times the width. And what's the width in the case? It's the bounds. The bounds give us our width. So if I have it in terms of x, then it's the first function. If I have it in terms of y, so again, if I am rotating around a horizontal line, horizontal, if I could spell horizontal, line of rotation. And then vertical line. Now, if I only have one function, okay, and I'm rotating around the axis, then I'm going to use my disk method. If I have two functions, or if I have two functions, yeah, then we're going to use the washer method, the second method, where again, you do need to identify what is furthest. Now, again, big R is furthest from the line of rotation. Specifically, what you're rotating around. Whatever is the furthest from where you're rotating around is your big R. All right. Any questions? How we do it?
Scrap that we did, we would have to put this one in the dissipation. Because we rotated around the y-axis, right?
Yeah, we'd have to use that.
What were you showing us on the graphs? This?
Which one? Yeah, that.
Yeah, like imagine like this, like they're solving for anything.
Yeah, no. Just right now, I just want to make sure you know how to set it up. If you can't set it up, then there's no point. The hardest part isn't going to be doing the integration because you can plug in your calculator or again do it by hand. You guys are doing really good with integration. Okay. All right. So the hardest part is setting it up. It is not solving for the integral. All right. So next page. Here are all the 10 steps to solve this.
Like what?
For one, shade the region bounded by the given curves. Make sure your region is literally trapped by the boundary curves and do not make your own boundaries. The x-axis and y-axis are not automatically boundaries. Draw the axis of revolution as a dashed line. Reflect the bounded region over the axis of revolution. Now shade the reflected region too. Decide the cross-section would be discs or washers. Write down the appropriate formula. Don't substitute into the formula yet. Choose a formula involving variable of x if the x-axis is horizontal, like I said. Or choose a variable involving y if the revolution is vertical or cross-sections should be taken perpendicular to the axis of revolution. For dis only, find the radius. It's a segment from the axis of revolution to the function. And usually it's the axis. Well, yeah. Let's function. All right. For washers only, find the outer radius. It's a segment from the axis of revolution to the outer curve. The inner radius is the segment of the axis of revolution to the inner curve. Determine the limits of integration. Be sure to use x values if the axis of revolution is horizontal, and use y values if it's vertical. Plug into the formula and then use your calculator or integrate by hand if possible. So,
Right.
yeah, use your T89. Anybody have a T89?
That's good. I think so.
See,
Small one, right?
It's this.
no, it's this big.
Yeah, no.
This is like from 2000. Okay, it's when I bought it. Literally, yeah, the year 2000.
You know, why my little world was not the go away the home. Yeah. Just like those high school.
Well, you'd have a slide rule. You'd have a slide rule.
Oh, what?
A slide rule. Look it up. It is a like triangular shaped ruler that they use for integration and all that fun stuff. Yeah, I've never had to use it. I worked with people who had. Maybe I stove about it. He's not. Okay. He might not have though, but I've worked with people older than him, and yeah, they talked about how to use a slide rule. I had a teacher who talked about when they had a computer, they didn't have, because again we didn't have internet. So if you had to save something, well, I grew up with floppy disks. Okay, yeah, she grew up with sheets of paper with holes punched in it, and that's you have to put it in the correct order. And if you ever get them out of order, you've just wasted everybody's time.
That's really.
Yes.
Wait, so you have to manually punch the information.
You'd have to manually insert the sheets of paper in the correct order for the computer to get the information.
That seems more inconvenient.
Yeah.
Is typing not?
It was all DOS. Do you know DOS? It's basically coding language now. What they consider to be coding language now. No, it's not binary, but it's command based. Okay. Yeah. Alright, so sketch the region bounded by the curve. So we have the function y equals x squared, the x-axis, the line x equals 2, then revolve it around each of the indicated lines in the figure. So, here we have graph of y equals x squared. So 1, 1, 2, 4. I think it's as far as I need to go. We can put that over here.
And then what?
And we have the line y equals, or x equals 2. So this line here. This is y equals x squared. All right. So we are going to take this shape bounded by these two lines, because we do have two lines here. So from 0 to 2. So we would integrate from 0 to, well, let me do it down here so we can see. So we would integrate from 0 to 2. All right. Now, if I'm rotating this around the x-axis, okay, that means that I'm also going to have this down here. Okay, where I have point and 1, 2, 3, 4. Right? And the area that I'm finding, or the volume I'm finding, be this right here.
Are you bounded?
Yeah, it's bounded from 0 to 2 because I'm rotating around the x-axis, and my two functions I have is just y equals x squared and x equals 2. So it's inside those two regions. Oh.
The y-axis.
We don't need it.
What about the part you reflect over X equals?
Because, let's see here. No, we don't need it.
You said that
That's a good question. It doesn't specify. So actually, that is a problem with this question. But we're going to say that we're just going to ignore the left half of the graph. Okay, so we're going to have the y-axis as also one of my boundaries.
do we also reflect over X equals 2?
Mm-mm. No, because it says the point of reflection is what A is. Now, what we have to ask first is going to be what kind of method are we going to use? Is this a disk method or a washer method? Disk because there's no hole in the graph, right? It's one solid shape. Okay, if I rotate this, it'll be a nice solid shape. So we'll be disk. Now, disk, if you remember, we're going to be using integral from a to b, or pi times integral of a to b of r squared dx. That's your disk method. So we have pi over here, 0 to 2. My radius is just the function itself, right? So just x squared. So x squared squared dx. Yep. So it becomes pi times integral of 0 to 2 of x to the fourth dx, which we can just do by hand. Pi. And you said it was what? Fifth from 0 to 2. Now, again, because 0 is just 0, we don't have to worry about it. But by plugging 2 to the fifth is 32.
Divided by 5.
So 32 pi, just leave us 32 pi over 5. Or if you want to do 6.4 pi, you can. Or if you want to do 20.106, if you just want to plug it all into a calculator and, yeah.
32.
Yep. So that's not bad, right?
You told me that I was not able to generate the thoughts to do those things.
There we go, I don't know.
So I was kind of following, but I'm not really.
I mean, that's good. At least, at the very least, you could follow, which is more than most.
When?
All right. So we're going to take the same function for part B. So here we have y equals x squared. We have 1, 2. Well, let me make that look better. 1, 2.
What?
1, 2, 3, 4.
Good morning. Yes.
All right. This time we are going to rotate over the y-axis. So it means we will have this other half over here.
No, we didn't with our side. Or
Now, my bounds, what are my bounds? They give us there's three functions that bind my function. Y equals x squared, x equals 2, and the x-axis. So it's still this area being rotated.
how should I remember that? Oh, because we're the bounds.
It's got to be bounded by those three functions. So what's in between those three functions? The y equals x squared, x equals 2, and the x-axis. That is what's binding my region. So this time I'm rotating around the y-axis, so I would have this over here.
Where the level. Lost.
So if I rotate this direction, so I rotate this way, there's a big old hole in my, yeah.
Now, how do we know that it stops at y equals negative 2? So infinity. I can see what.
Because it's this function being rotated. You have to mirror that function. Yeah. Now, in this case, I'm rotating around a vertical line or horizontal line. Which means I need my function in terms of what? And y. Anytime I rotate around a vertical line, I need my function in terms of y. So since y equals x squared, that means x is equal to square root of y. And again, it should be what? Plus or minus, but I only use what? Plus because I'm only in the positive side. Because here my x is all but positive. So it's just the plus. I don't have to worry about the minus. Okay? So that's the function I'm rotating. Is that my outer function or my inner function? Oh.
No clue. What? That's your in function.
Yeah. Is that function, let me zoom in so we can see this a little better. That's not zooming in. That's where I am now.
It's a little on.
Where's my fucking...
Why can't we just do this method and then subtract the other business method?
That's what we're doing, technically. That's what the washer method does. So, here, this is the closest. This graph here is the closest to my line of revolution, right? Because I'm revolving around this line right here. So that's my little r. Little r is the square root of y. What's my big R?
X.
4, 2.
Yeah, x equals 2.
Distance from here to here.
Oh, that makes sense.
Since I am doing, again, the washer method is basically taking the disk method and taking the big disk minus the small disk. So if we do that, again, it's still going to be pi, all right, times the bounds from a to b of my big disk squared minus my small disk squared, and in this case, dy. Okay? So I already said what both these were, right? So it's pi bounds. Now, again, my bounds need to be in terms of y, not x. So what are my y values for these bounds? 0 to 4. So don't forget to put the bounds in terms of y as well. So my big R was 2 squared. My little r was the square root of y squared, dy. So we end up with the integral from 0 to 4 pi times the integral from 0 to 4 of 4 minus y.
And then you just do
Just be.
It's just 8 pi.
Looking for you get 16 minus, yeah, 8 pi.
Hard to find volume.
The outside of the problem.
So let me do this. We're taking this region right here and we are rotating it around. Okay? So rotating around. So it's this right here being rotated around all the way around. All right? So what I have basically is a cylinder with kind of a parabola shaped dome being cut out of it.
Oh, okay.
So the cylinder volume would just be the 2. Okay? Well, 2 squared times pi times the width here. All right? Minus the volume of that rotating parabola.
Okay, I was just confused at work.
Again, it's really difficult to put a 3D object on a 2D plane. All right, so we got 2 of them down. All right, third one. Now, the third one we have our function, our parabola at 1, 2. Well, 1, 2.
Oh my God.
It's the same answer. Yeah. No way, and it's the same thing. It's
This time we're rotating over what? So we're taking this shape and I'm rotating it over x equals 2, which means it's going over here. So that's what I'm rotating. That's the shape. So it kind of makes like a sorry piece.
last problem.
Mm-hmm.
Well, the same
Oh,
answer.
it's 2 minus.
Not the same area.
It's the other one. So
That's a diff, not.
This is a disk method. Okay, not a washer method. But what's the center of my disk? What x equals 2. Okay. So the radius of my disk would be that 2 minus the function. I'm still rotating across a vertical line, right? So what's the function? Yeah, it has to be f of y. So here is x equals 2, and this is x equals square root of y. So my radius, r, and again, we're doing the washer method, so r will be 2 minus the square root of y. If I was trying to describe this, let me zoom in here so I can see this and put this in a different color. If I was trying to describe this length of line right here, that would be, again, it has to be in terms of y because it's horizontal. That would be 2, because that's the distance from the y-axis to that point is 2, minus the function. Because that's the whole length, 2. That's the length for the function, square root of y. So here would be 2 minus square root of y. So we are going to do that washer method. Not washer method, disk method. Now again, it still needs to be in terms of y, so what are my bounds? 0 to 4 of 2 minus y squared dy. Now this one is a bit different, because when you multiply that out, what do you get? And again, how about we just put this in a calculator? Let's not worry about, oh, where's my square root at? Yeah, where'd my square root go? Just put it there. I gotta swear I put the square root of y there, but hey. So let's just put this in the calculator because I don't want to do this by hand. All right, clear. We have pi. So second pi integral from 0 to 4. Parentheses 2 minus square root. Again, we can put it in terms of x. It's fine. It's just a variable at this point. All right, close the parentheses, squared. And we get 8.378.
No.
Oh,
We put pi in there. So yeah. What would it be without pi? Okay, so you can have 2 and 2/3. So you could do what? 2 and 2/3 is what? 8/3 pi, if you wanted.
24 minus 8 is 3.
Cube.
Yeah, the cube.
You do this by hand. 1 0 to 4 of 4 minus 2 square root of y
It's 8.
plus y.
Wait, where did the 2 go?
That's right, it should be 4, you're right.
Yeah, I got 4 minus 4 root y plus y dy.
And the integral of that would be
4y minus 8/3 cubed root of y squared.
Not 8/3. Oh no, it would be, yeah, 8/3. You're right. 8/3. So we have y squared 0 to 4.
Plug 4 into that. 16 8/3 cubed root of 16.
Have 1/2. Yeah. No, it's not 3. This is still to the 3 halves, so this is square root of cubed, not the cube root of squared. Yeah, so square root of cubed. So if you plug in 4 minus 8 over 3 times 8 minus 8. I got, see here, 8 minus 64 over 3. That's not right.
It should be 4 times 4, which is 16, minus 8/3 of 8. So it should be 16 minus 64 over 3 plus.
Plus 8. Plus 8. I got minus 8. So that should be 24 minus 64 over 3.
Yeah.
Which would give you times 3, 72 over 3 minus 64 over 3, which is, 8 over 3, which is what we had. Yeah. So you can do it by hand, but no, if you don't have to, don't. Again, you have to be careful though, because some of your tests is gonna, not like this test, but your AP test will be non-calculator. So you do need to be able to do stuff by hand. How much time we got left? All right. So we do have, we have one more page to do. We can do that on Monday or Tuesday. We'll do it on Tuesday instead. If you want to go ahead and look over the homework, feel free to look over the Delta Math homework. We'll probably spend Tuesday finishing this and answering questions on Delta Math homework.
When is our test?
I know.
It won't be next week, it'll be week after. Then there's just chapter 9 and 10 left.
How do I start these from the first one? I can see it, so I can do
Oh yeah, multiply, right? I
Yeah.
can know the variables on both sides. Oh my gosh.
this stuff.
TY. No, that's just the solid. Oh yeah, that is kind of a different shape.
Were you gonna do something with this shoe?
No, this is the other. That is you could. Yeah, that you can kind of see if it's sliced horizontal. There's another one I have, which is a cylindrical shell method, which
Would this be
creates
like
cylinders.
this would be like negative x squared, right?
Yeah, if you took
If it went
and then shifted it over, or rotated around. Let's say y equals. And if you make it simple, you can say 1 minus x squared, and then rotate it around x equals 1 or x equals -1. Or actually further, because you have a hole, so x equals 2.
yeah, that makes probably
Right? Okay, this is all that. Okay.
Kind of makes sense.
So bring this over, we end up with times 1 over 3y cubed equals 1 over cosine pi x dx. Right? So let's the equation 3. Okay. So
This question goes, right?
This is 1/3 y cubed dy. The integral of that would be add 1, so 1/12 y to the fourth. It's equal to the integral of this, since that is what cosine is. 1/2 cosine is secant. And the integral of secant x,
Pi x.
pi x. So secant pi x.
That is
I don't think there is one. I know the derivatives.
yeah, it's in like the weird tan one, like 1 plus tan. Or
Yeah,
something.
but it's that.
Like, say, hold on, what was? The book that was mentioned besides that. It's one second, reading
Instruction. 21. Routine.
yeah, like. Anyway, I'm sorry. There's a limit.